For over a century, delivering electricity required a strict rule. You needed a closed, continuous physical loop of metal to connect the power source to your device. Modern wireless charging breaks that physical loop. You place a device on a pad, and power flows through solid plastic and empty air. But this technology relies entirely on laws of electromagnetism discovered in the 19th century by physicist Michael Faraday. Engineers haven't eliminated the rules of electricity. They have substituted a physical copper wire with an invisible magnetic bridge. To understand how energy can cross an empty gap between two objects that aren't touching, we can look at a mechanical equivalent. Imagine two desk fans facing each other. If you plug in the first fan and turn it on, it blows air across the room. That moving air hits the blades of the second, unplugged fan, forcing it to spin. Wireless charging works the exact same way. Only instead of moving air, the charger generates a fluctuating magnetic wind that pushes electrons. The journey begins at the wall outlet. Grid power enters the charging pad as a sluggish, low-frequency electrical current that is completely incapable of jumping across an air gap. Inside the pad, an inverter circuit takes that sluggish power and transforms it into a highly energetic, high-frequency alternating current, or AC. Alternating current is an electrical flow that rapidly reverses its direction. This rapid current is then pushed through a tightly wound spiral of copper wire called the transmitter coil. According to Ampere's law, a principle stating that an electric current flowing through a conductor produces a magnetic field, this coil generates dome-shaped ripples of magnetic flux that radiate upward. Because the current is rapidly alternating, this magnetic field constantly reverses its polarity. It expands and collapses thousands of times per second, creating our pulsing magnetic wind. The charging pad doesn't actually store any power. It is strictly a translation device, built to turn standard grid electricity into a localized, vibrating magnetic bubble. Now we need a way to catch that energy. That happens inside the smartphone, which houses a thin, carefully wound receiver coil. This technical simulation shows a cross-section of the magnetic field in a wireless charging system. The pad is on the bottom, and the phone is on top. When the pad's fluctuating magnetic field washes over the phone's coil, it triggers Faraday's law of induction. This law dictates that a changing magnetic field will physically force electrons inside a nearby wire to move. Looking at the intense pink and purple density zones around the top receiver coil, we can see the exact moment of transfer. The magnetic field induces electron movement in the phone. Power has successfully crossed the air gap. The smartphone catches these invisible magnetic waves and converts their kinetic energy back into an active electrical current. But there is an immediate problem. The newly induced current is a chaotic, oscillating, alternating current. If you feed that directly into a phone battery, it will destroy the device. To fix this, the phone uses a rectifier circuit. A rectifier is a component that translates the chaotic, back-and-forth AC wave into direct current, or DC, a smooth, continuous flow of electricity moving in a single direction. Before this power reaches the battery, it passes through a final checkpoint. A voltage regulator monitors the line, ensuring the exact right amount of smooth DC power flows through to prevent overcharging. The lithium-ion battery has no idea it is being charged wirelessly. It simply receives the perfectly filtered direct current it requires to function. If this transfer is so sophisticated, you might notice that wireless charging is often slower and generates significantly more heat than using a standard cable. Magnetic transfer has strict physical limits. Up to 30% of the energy from the pad is lost as leakage flux. Leakage flux refers to the magnetic field lines that completely miss the receiver coil and scatter their energy into the surrounding environment. That leaked energy, combined with the internal electrical resistance of the coils, physically manifests as thermal energy. The devices heat up rapidly. Modern smartphones have strict safety protocols. When their internal temperature sensors detect too much heat, they automatically throttle down the charging speed to protect the battery chemistry. The convenience of dropping your phone on a pad comes with the physical cost of lost energy and a constant battle to manage heat. The biggest enemy of transfer efficiency is spatial misalignment. If the phone is placed even a few millimeters off-center, the magnetic connection drops, leakage flux spikes, and heat generation increases. Engineers solved this in newer standards, like Key 2 and MagSafe, by adding physical magnet rings around the coils to force perfect concentric alignment. This forced alignment maximizes the surface area overlap between the transmitter and receiver. It minimizes magnetic leakage, reduces heat, and drastically improves charging speed. By mastering these invisible electromagnetic forces, engineers have managed to put a microscopic, fully functioning power transmission plant right in your pocket.